Welcome to you as we continue our study of polynomials, looking today at complex and rational zeros of polynomials. You guys have talked about roots and zeros of polynomials for a while now, of course, but maybe it's just kind of soaking in that sometimes there are numbers that make polynomials equal zero that are complex numbers. In fact, we have a theorem on conjugate pair zeros of a polynomial, kind of a awkward name here, but it says if a polynomial f of x of degree n, where n is bigger than 1, has real coefficients, and if z equals a plus bi, b not 0, is a complex zero of f, then the conjugate is also a 0. So we've got two complex numbers here, z and its conjugate z bar. We read this as z bar, and so if we look here at our example, it says a polynomial with real coefficients and a leading coefficient of 1 has the given 0 of -4 plus 3i and degree 2. Express f of x as a product of linear and quadratic polynomials that are irreducible over the real numbers. Well, so let's point out here that if -4 plus 3i is a 0, then -4 minus 3i is also a 0. Now let's just, for a second here, let's go over here in a thinking bubble. I've got this polynomial x squared plus 5x plus 6 equals 0. Let's remind ourselves of a couple things. X plus 2 times x plus 3 equals 0. X plus 2 equals 0. X plus 3 equals 0. X equals -2, x equals -3. So what we're doing here is we are taking, in this example, we're taking these roots and we're going back to this polynomial. So we're starting here and we're working in reverse. So I'm going to start with my roots, x equal -4 plus 3i, x equal -4 minus 3i. And so here we go. We've got x plus 4 minus 3i, that equals 0. We have x plus 4 plus 3i, that equals 0. And so now, look what we did. Once we got these guys set equal to 0, then we multiplied them together. So here we go. X plus 4 minus 3i times x plus 4 plus 3i. This equals 0. Alright, well now let's take a look and see what's going on. We've got A and B. A and B. Take a look at this for a minute, would you? And let me switch colors of ink here just for a second. You see how this is A minus B and this is A plus B? We know that if we multiply A minus B times A plus B together, that we're squaring the first minus the square of the back. So in this format, we're looking at the difference of two squares. Alright, and so what we're doing here is we're squaring the first guy, x plus 4 quantity squared, and we're squaring the back guy, 3i quantity squared. Okay, and we don't really need our equal 0 anymore. We're just writing a polynomial. So I'll get rid of that, actually, but that kind of helps us understand where we came from, how we got here now. And so, well, let's see. It says expressed as a product of linear and quadratic polynomials with real coefficients. So here we go. This is our factored form, and something like this, and this would be okay. This would be okay for an answer. But let me just point something out a minute. If we expand on this, x squared plus 8x plus 16 minus 9i squared, well, this is x squared plus 8x plus 16 minus 9 times -1, x squared plus 8x plus 16 plus 9 equals x squared plus 8x plus 25. Here's my polynomial. Here's my polynomial, and if I were to now set this equal to 0, okay, so let's make a note here. Note x squared plus 8x plus 25 equals 0 has solutions x equal, where'd we go here? X equal -4 plus 3i, and x equal -4 minus 3i. Alright, so there is my polynomial expressed as a product of linear factors, linear and quadratic polynomials. So here's my answer, but I want you to see what else can be done with this information. And I wouldn't take off if you multiplied it on out to this. I'm just saying that this in the black is what I would be looking for there as a solution. Let's take a look here. We've got another polynomial here. And notice a few things. They're telling me that x equal 3 plus 5i is a 0. Well, if 3 plus 5i is a 0, then 3 minus 5i is a 0. Because of what we said earlier, if one imaginary number is a 0, so is its conjugate. And then we are told that -1 minus I is a 0. And we are told that -1 plus I is a 0. Alright, so with that in mind, if those are all my zeros, then x minus 3 plus 5i is going to be a factor. X minus 3 minus 5i is going to be a factor, and each of these equals 0 then at this point. X minus -1 minus I is a 0, and x minus -1 plus I, that's a 0. Okay, and so what we're going to do here is take all of these factors, x minus 3 plus 5i, x minus 3 minus 5i, x minus -1 minus I, x minus -1 plus I. Alright, and so then we can clean these up just a bit. And guys, I'm using brackets here because I'd already used the parentheses. It really doesn't matter if we go brackets or parentheses. I'm going to get rid of these inner parentheses now. This is x minus 3 minus 5i, x minus 3 plus 5i, x plus 1 plus I, and x plus 1 minus I. And so here we go. We have our product of linear factors. Okay, again, I would point out here that if we needed to do something a little bit more with this, once again, let me illustrate here that what we have is a minus b and a plus b. And here we have a plus b and a minus b. So we could even go, x minus 3 squared minus 5i squared times x plus 1 squared minus I squared, if we wanted to. Okay, we could even do that. And so what this would give us, x squared minus 6x plus 9 minus 25i squared times x squared plus 2x plus 1 minus -1. And so I've got x squared minus 6x plus 9 plus 25, because we remember I squared is -1, times x squared plus 2x plus 2 And so we're looking at x squared minus 6x plus 34, x squared plus 2x plus 2. And just to give you an idea here of what polynomial would have this as the roots, we can expand this on out. This is x to the fourth plus 2x cubed plus 2x squared minus 6x cubed minus 12x squared minus 12x plus 34x squared plus 68x plus 68. And so we've got x to the fourth minus 4x cubed. Let's see here, 34 plus 2 is 36, minus 12 is 24, x squared plus 56x plus 68. So there's the polynomial that has for its roots 3 plus 5i, 3 minus 5i, negative 1 minus i, and negative 1 plus i. Alright, so let's move along to our next theorem here. And we look at it, and let's say that we've got an nth degree polynomial, maybe a cubic, fourth degree, fifth degree, something really big. Let's take a look at what our theorem says here. If the polynomial has integer coefficients, and if c over d is a rational zero of the function, such that c and d have no common prime factor, in other words, c and d, that fraction's been reduced, then the numerator c of the zero is a factor of the constant term a sub naught. So right there is my a sub naught. And the denominator d of the factor, or of the zero, is a factor of the leading coefficient a sub n. So here's my a sub n. It's equal to 2 in this particular problem. Alright, so what we need to think about here as we get ready to do this problem, we're going to look at the factors of a sub naught, okay, and the factors of a sub naught are plus or minus 1 and plus or minus 7. Now my factors of a sub n are plus or minus 1 and plus or minus 2. Remember, a sub naught equals 7, a sub n equals 2. Alright? And so what we're going to do is we're going to make a list of the possibilities of a sub naught over a sub n. So plus or minus 1, plus or minus 1/2, plus or minus 7, plus or minus 7/2. Alright, so all the factors of the constant 7 right here. All the factors of this leading coefficient right here. And then I'm looking at all the possible combinations of factors of a sub naught over a sub n. Now, I'll tell you what I like to do. The best purpose, I think, of this particular theorem anymore is to help us in uncovering not just the rational roots, but also any irrational roots that might exist. And so what I'm going to do now, I'm going to use the calculator actually to help us evaluate what's going on. So let's open our calculator up here, and I'm going to go to the y equals screen and type in 2x to the 5th plus 3x cubed plus 7. And what I'm going to do here, now that I've got that in, I'm going to quit out of this and I'm going to go to my y variables. Alright, y variables here, and I'm going to call up y1. And the first thing I'm going to do actually is I want to take a look at the graph of this. I'm getting ahead of myself here. Pardon me. Let's take a look at the graph of this. Now, it looks like, okay, it looks like here, this is my standard viewing window, it looks like we've got a 0 right there about -1, doesn't it? Alright, and if we look back here at our notes, we can see that -1 is one of the possibilities for a 0. So what I'm going to do, we can check -1 out fairly easily by hand, actually, but we went to the trouble to graph it and take a look at it real quick. I'm going to go back here to our home screen, and I'm going to evaluate y1 at -1 and see if we get 0. And we don't. We don't. Okay. When x is -1, we get 2. Notice, let's look at our window here. Alright, -10 to 10 to 1, -10 to 10 to 1. This is our standard viewing window. But this is growing very, very, very quickly right here. And folks, I'll be honest with you, this theorem was really, really handy when we didn't have some of the technology that we have now. You know, now we can plug in, we can look at the graph, and of course we could get the 0 if we wanted to, and what we'd find if we do the 0 on this, and we could just do it, you know, second calc, 0, and so my left bound, get over here a little bit to the left, we hit enter. My right bound, I hit enter, and I hit enter a second time. Notice, yeah, this decimal terminates, but it terminates only because the calculator doesn't have enough room for it to keep going on out. So what we can note here is that these are the possible rational roots but using this info and the graph, we see this polynomial has no rational roots. And we'll take a look now at, well, for class discussion, look at 14, and then for homework, look at 11 and 15. Certainly, as always, if you have questions, bring those into class. We'll be glad to take a look at them. So let's see here. As we move ahead, now we're going to look at our next theorem. This is a theorem on expressing a polynomial as a product of linear and quadratic factors. Every polynomial with real coefficients and positive degree n can be expressed as a product of linear and quadratic polynomials with real coefficients such that the quadratic factors are irreducible over R. So what we're saying here, folks, is that of course linear factors, we can't break those down anymore, and any quadratic factors that we have, those will be prime. We won't be able to break those down anymore over the real numbers. Any solutions would be imaginary. So let's take a look here at our next polynomial. Now, remember what's going on, okay? A sub 0, those are all the factors of 24. So plus or minus 1, plus or minus 2, plus or minus 3, 4, 6, 8, 12, 24. And then a sub n, okay, a sub n, we've got all the factors here of 1. So, well, that's kind of exciting. Plus or minus 1. Alright, now, I'm going to be honest. The need for some of this with the advent of the graphing calculator, a little questionable. Depending on where you're going, what field you're going into, what emphasis the teacher wants to place here, you might very well be doing all of this with technology. On the other hand, if you're looking at a more theoretical math perhaps, or some analysis in your future, maybe some actuarial sciences or something like that, This is a skill that bury it deep in the toolbox. Honestly, probably won't use it a lot, but we want it to be there. Alright, so again, I'm going to make a graph here of this. So going back to my calculator, x cubed plus x squared minus 14x minus 24. And remember, guys, this is a cubic polynomial, so we're looking for 3 solutions. And it looks like that maybe -3, -2, and 4 from the graph. That's what it looks like. Might be the case. Now, let's take this opportunity. We suspect x equal -3, x equal -2, x equal 4 to be the solutions. That's what we expect. Now, let's just take this opportunity to use one of the techniques we've learned earlier in this chapter to verify that. Let's use synthetic division here. We've got factors of -3, -2, or roots rather, we think of -3, -2, and 4. Well, let's just check that out. Alright, let's use a little synthetic division here, pulling the coefficients from the polynomials. So 1, 1, -14, -24. Remember how synthetic works. This comes down, multiply on the v, we add down, that's -2, multiply on the v, that's 6, we add down, that's -8, multiply on the v, that's 24, and I'm left with a remainder of 0, so x equal 3, x equal -3 is a solution. Let's check out -2 once again with synthetic division. 1, 1, -14, -24. The old Price is Right. The 1 comes on down. -2 times 1 is -2. Add down. That's -1. Multiply on the v. There's a 2. Add down. -12. -2 times -12 is +24. Guess what? X equal -2 is a solution. And then let's check out 4. See if it's a 0. So again, line up the coefficients. 1, 1, -14, -24. 1 comes down. Multiply on the v. Add down. Multiply on the v. Add down. Multiply on the v. And once again, we have a remainder of 0. X equal 4 is a solution. And we have our 3 roots of this cubic equation. Alrighty, and that was so much fun. Let's do it again, okay? Once again here, let's take a look at my factors of my constant. So a sub naught, my factors of 18 plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. And then my factors of a sub n. Well, we got plus or minus 1. Alright, so now, just as I did before, we're going to ask the graphing calculator to help out. I'm going to go back here and we'll take a look at this. Clear this out. So we've got x to the 4th minus x cubed, minus x cubed minus 9x squared plus 3x plus 18. Alrighty, and so to the graph we go. Ooh, let's take a look at this. It looks like that we might have zeros at -2. Yeah, I don't know about +2. Might have to check that out. -2, maybe 2, and there's 3. So let's see here. X equal -2, we think. X equal 2, maybe. And x equal 3, perhaps. Alright, now we're going after all the solutions here, guys. all the solutions. So let's see what we're going to have to do here. Let's put negative 2 in. Alright, 1, negative 1, negative 9, 3, 18. Bring down the 1, multiply on the v, that's negative 2. Add down, that's negative 3. Multiply on the v, that's positive 6. Add down, there's negative 3. Multiply on the v, that's 6. Add down, that's 9. Multiply on the v, that's negative 18. And there's the 0. So we have found that x equal negative 2 is a solution. Alright, x equal negative 2 is a solution. Now, what this means is negative 2 is a solution, and we have reduced this polynomial to x plus 2 times x cubed minus 3x squared minus 3x plus 9 is what we've reduced this polynomial to. Alright, so now we've got it reduced to this. Well, let's look for factors of this particular polynomial. But let's be a little bit smart here. I've mentioned in these lectures before how I want to work smart, not necessarily hard. We may have to work hard from time to time, but I want to work smart here. Now, a little bit ago, it sure looked like 3 was a solution of our original polynomial. 3 looked like it was a solution of this. Well, if 3 is a solution here, then 3 ought to be a solution here. So let's see if that'll help us any. Let's do the synthetic division. 1, negative 3, 9. And here we go once again. We're going to add down. This is 1. Multiply on the v. This is 3. Add down. This is 0. Multiply on the v. That's 0. Add down. And multiply on the v. Hey, what do you know? This is getting pretty exciting. So x equal 3 is a solution, and we know, check this out guys, we know that x squared minus 3, because this is x squared plus 0x minus 3 is a factor. Alright, well, if x squared minus 3 is a factor, then that means that we've got x plus 2, x minus 3, and x squared minus 3. This would equal 0. We've got 2 of our solutions, 3, negative 2. Now all we need to do is set this x squared minus 3 equal to 0. X squared equals 3. X equals plus or minus the square root of 3. And so my zeros or solutions here to this are x equal negative 2, 3, and plus or minus root 3. And of course, if you have questions on those, bring those to class. But this is a nice problem. It helps me arrive at some of the irrational zeros that would be a little more difficult to arrive at without this theorem. Let's take a look here at example 6. And again, we're asked to solve this. Let's get our factors of a sub 0. Alright, well, we're looking at plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. And then we need our factors of a sub n. So we're looking at plus or minus 1 and plus or minus 3. Okay? And so once again, you know what I'm going to do? I'm going to grab that calculator. We've got it. Let's use it. Here we go. And so we've got 3 x cubed minus x squared plus 11x minus 20. And we'll take a look at the graph there. Well, let's see. The only possibility looks to be just a little bit bigger than 1, doesn't it? Well, let's check our list here and see if maybe we can come up with something a little bit bigger than 1. Now, let's see. We've got 1 over 1, 1/3. We're going the wrong direction here. How about 4/3? Let's try x equal 4/3. Let's see what we might get here. Alright, let's put 4/3 in the box. List my coefficients: 3, -1, 11, and -20. We're going to bring the 3 down, multiply on the v. We got to multiply fractions here, guys, but I think we're up for it. 4/3 times 3 is 4. Add down. That's a positive 3. Multiply on the v, so 4/3 times 3 is 4. Add down. 11 plus 4, 15. Multiply on the v, 4/3 of 15 is 20. And what do you know, we add down, we get 0. So here's where we're at. Alright, we know that x minus 4/3 times 3x squared plus 3x plus 15, these are factors. And have you noticed, of course, with the synthetic division, remember, we started with a cubic, so this drops this power down one, so this is now a quadratic. We've got one solution, and now we're going to look for our other solutions. 3x squared plus 3x plus 5 equals 0. Alright, well, this is not going to factor, so let's bring on the quadratic formula. -3 plus or minus the square root of 3 squared minus 4 times a times c all over 2 times 3. -3 plus or minus the square root of 9. Well, let's see here, minus 60 all over 6. Coming up here, x equals -3 plus or minus the square root of -51 all over 6. -3 plus or minus I times the square root of 51 all over 6. And for class discussion, if you'd take a look at 22 and 26, and then for homework you can see the list of problems, that would be fantastic. We'll take a look at those. And guys, there's some of this stuff that might be a little bit different. So if you've got questions, please bring those up. Thank you.